Welcome back to week 2. I'm actually awake this week, so the lectures will be much faster, I reckon. So hang on to your hats. No, they'll just probably be much wafflier. I don't know. They'll be whatever comes out when I'm actually awake. That's what they'll be. So last time we talked about global Galois groups, which is a fancy way of saying Galois groups of number fields. And the way we're going to understand these global Galois groups is, first thing I'm going to do is I'm going to take this finite group here, gal L over K, where K is like the rationals and L is whatever, the splitting field of x cubed minus 2. And we get a nice finite Galois group that we all thought we understood. And the first thing I'm going to do is I'm going to give every element in that Galois group infinitely many names in an attempt to throw you off the scent. So this is the original plan. We have gal L over K contains this D. So remember, I choose a random prime downstairs. Curly P is a prime ideal of K, and now I suddenly have, and then capital P divides curly P, and I suddenly have this subgroup. Okay. So this fact that I alluded to last time. So this fact is, if I've got sigma. If I've got sigma turns out to be in this subgroup, dp over p, dp over p, then what does that mean? Then when you think about it, by definition, sigma is a map from L to L, and sigma will send OL to OL, because just that's life, isn't it? OL is some intrinsically defined thing. And then sigma, well, normally sigma definitely sends little curly p to itself because it's in gal L over K, right? So sigma fixes K, and sigma fixes, by fixes I mean fixes pointwise, right? Fixes OK. I don't just mean it maps OK to itself, I mean it acts as the identity on OK. So it fixes this stuff pointwise. There, and then we've got this sigma, so sigma fixes curly P, and normally some random element of the Galois group would permute all those primes above curly P, like complex conjugate. Oh, I should say, I'm going to do review 4 till 5 again today. I'll do examples of this stuff. Right, no more examples. Okay, forget examples. What examples you have to come 4 till 5? Sigma fixes P, but sigma does send kind of capital P to capital P. I am actually serious. I'm going to go, I don't quite know. When I was your age, I'd kind of picked up this stuff already, but maybe not any of you did. But on the other hand, some of you are much older than I was when I was your age, and so you probably almost certainly know it. But when I say when I was your age, what I actually mean is when I was a first-year graduate student, because those are the people that are supposed to be here. And then all the other people that are, these are people that have got here for various other reasons. Do remember that you weren't my age or something. So sigma goes from P to P, and so this is kind of good, right? So that means sigma kind of says OL mod P to the n to OL mod P to the n. So sigma induces some map, so sigma gets some map from OLP, the completion, to itself, and so sigma maps LP to itself, right? And fixes KP, sorry, fixes capital K P there. So you see, so sigma is really in this gal LP over KP, right? Right, and that turns out to equal dp over p, in the sense that they're canonically isomorphic. So, okay, this needs work. This is a heuristic sketch, but this is true, right? You have to do some counting and make sure that everything works out fine. But this turns out to be, you know, this, maybe I should say, this needs checking, right? But I'm not going to check. The checking is just boring algebra, and I want to do interesting algebra. So that's how it works, and the great thing is that this global Galois group that we're trying to understand magically contains this local Galois group, about which we said a great deal of stuff in the first part of the course, much of which might have been incomprehensible to some of you, but it doesn't matter because we only need the lightest of, we only need a tiny amount of the stuff we were talking about. So this dp over p, therefore this dp over p contains some inertia subgroup, right, ip over p, which is, I guess, that would have been in the old notation ILP over KP, right? There's the inertia subgroup, and the miracle is, for a given, in this global situation, in this global situation of number fields, L over K, we have a global discriminant, right? If we have this delta is the discriminant of L over K, So this is, if you like, somehow the correct way of thinking about the discriminant is an ideal of OK. And if P doesn't divide delta, I should say this is non-zero. And if P doesn't divide delta, that implies that P is unramified. That implies that IP over P is actually the trivial group for all P dividing P. And that's the same as saying that IP over P is the trivial group for one prime ideal capital P dividing P, because by transport of structure, all this factors as every single prime that factors, that divides little p, they're all kind of isomorphic to each other, even though they're not the same. There's some element of the Galois group that maps one prime into the other one, so they all become isomorphic. So these if I think of little p as fixed and capital P as varying around, I get a whole bunch of these inertia groups. What I'm saying is they're all abstractly isomorphic. So if one of them's trivial, they're all trivial. So this is just a general phenomenon. In you can tell whether you're doing number theory or not, because if something's ramified at infinitely many primes, then you're probably not doing number theory anymore. Number theory, things tend to be unramified outside a finite set of primes. And that finite set of primes is often called capital S. But at this point in the argument, it's called the set of primes dividing capital delta. So that's good. So therefore, for all but finitely many primes, therefore, for all P not in some finite set, S, which is the primes dividing delta, the primes of OK dividing delta, the discriminant of L over K. So for all those primes not dividing delta, we get for all primes of P a cyclic group, right? dP over P. Oops. We get capital dP over P. That is a cyclic group because it's a local Galois group where the inertia group is trivial, right? So this is generated by Frob capital P, right? Because this group is really dP over P modulo IP over P. Because this inertia group is trivial. And this is the Galois group of the residue field, right? This is Gal. What notation should we use? I use little k. Little k has constantly denoted a residue field in this course, hasn't it? So I can put k, I guess I could k capital P over k little p. There. You see, because this local Galois group is unramified, and so capital LP has a residue field, little kp, and capital Kp it's got residue field, little kp, and there's that Galois group. So that's the structure. I mean, one might argue that seeing examples doesn't really teach you anything, right? Because the theorems are all general. I'll do some examples at 4 o'clock. I guess I should maybe do you know what? I will do one example because there's an example that we all have to keep in mind. Oh, let me say one last thing. I'm still talking about the stuff I said last time, really. I guess it's just so fundamentally important that I just need to make sure. This is an element, right? So this, again, something that I remember confused me at this time. So P is upstairs, right? P is upstairs. Upstairs is a notion due to Grothendieck. This is, again, another fabulous thing, right? Before, in the 1950s, when you look at papers, maps always went from left to right. That was the direction of a map. And one of the many things that Grothendieck did when he introduced algebraic geometry was he introduced the notion of maps. Maybe this also comes with also comes with what's the word I'm looking for? Progress in our ability to do mathematical typesetting. But the idea is that there should be some map down from some scheme to some base scheme or something. Apparently this notion of maps, I think it's like Illusis, I heard Illusis say this in one of Grothendieck's kind of memorial. When Grothendieck died, a lot of people said a lot of things. Emile Louzy said that Grothendieck started drawing maps downwards. But for Grothendieck, everything was a scheme, right? And maps between scheme is a speck of a ring, and when you take the specks, then the arrows go the other way. So which way do the maps go for us? I've got fields L and K. K is a subfield of L, you see, so K lives in L, right? So if I'm drawing rings, the maps go this way. But because I'm inspired by Grothendieck's idea that sometimes maps need to go downwards, so you see I get speck of L. I get speck of L going down to speck of K. So in my mind, when I have an extension of fields, the bigger field lies above the smaller field, you see. So P is upstairs, and that means that P is in speck of OL, right? P of upstairs, we get an element. We get an element frob P in gal L over K. So that's what happens if you're upstairs, but the problem is I'm not very interested in upstairs, especially as upstairs is going to be varying. I might want to do gal K bar over K, and then we kind of lose all track of what's upstairs. So really, we want some invariant that goes downstairs. So curly P downstairs. And now here you see there's an issue, and this is where I finished last time. There's an issue because P is a prime ideal downstairs, and I need to choose a capital P above it before I can do this calculation. So I choose a capital P above it, and I get an element, and then my friend decides to choose another one, and they get another element. And that's kind of a pain, but it's all right, because there's something in this global Galois group that maps my choice to their choice. And if I then kind of conjugate everything around, I'll see that my frob P turns out to be conjugate to their frob P. So P downstairs, you get a bunch of conjugate elements. Get a bunch of conjugate elements. Frob capital P for capital P divides little p for capital P upstairs, right? And you see you get different ones, right? And you take some random element of gal L over K and you conjugate frob P by it, you'll get frob P primed, where P primed is where the Galois element sent P. So that's really a conjugacy class, right? We get a conjugacy class. There, frob P. And that's called frob curly P downstairs. So there's abusive notation, right? This is operator overloading. I've got frob, and I can apply it to a prime downstairs and get a conjugacy class, or I can apply it to a prime upstairs and get an element. So there we go. It comes with all the associated risks of operator overloading. Well, there you go. So we need to do careful type checking. Great. So I've just written down, I lied to you. I said I was going to give all the elements infinitely many names, but in fact I've just given all the conjugacy classes infinitely many names. So here's a fact. So for just a general finite Galois extension L over K, given L over K as above, this is just an abstract Galois group, gal L over K. This, I've written, given L over K as above, every conjugacy class in gal L over K turns out to be named infinitely often. Every conjugacy class C in gal over K turns out to be equal frob curly P for infinitely many primes. For infinitely many primes P. That's not just fact, that's called Chebotarev, well, that's a very weak form of the Chebotarev density theorem. In fact, maybe I'll tell you how this is proved. Well, that's a silly thing to say. Let me tell you a stronger statement, which turns out to be what's actually proved. So it's not just that we get infinitely many frob P. In fact, the density in some precise sense. But this precise sense involves analysis, and I've already told you that I don't do any analysis. So there's some way of defining a density. I think it's just counting the number of primes with norm less than x or something. Don't push me on it. It is that. In fact, the density of, it doesn't matter. It doesn't matter. We'll never use it. I don't know what it is. That's proof, right? You don't ever need to use it. In fact, the density, unless you're, I don't know. You might need to use it. The density, just don't worry if you don't understand it. In fact, the density of primes p, in some well-defined sense that's been known for centuries, the density of primes p, such that from p is c, is in fact just the obvious thing. You imagine that the frob p's are actually elements from you actually pretend these are elements, and I'm taking random elements of my group and seeing if they land in C, and the chances that that's going to happen are the size of C divided by the size of G, right? So this kind of frob is like some strange quantum mechanical principle where frob p spits out an element, but you don't know which one it is. You only know which conjugacy class it is, but you have to pretend that it's a sort of secret quantum mechanically defined cat-like element. And if you actually open the box, you'll see which one it was. Oh, the Galois group. Sorry. G is Gal L over K, and C is a subset of G, you see. There. So this is some sort of quantum mechanical principle. But I think the proof doesn't use quantum mechanics. It uses analysis or something. Anyway, so that's great. So in fact, the upshot is, if I want to tell you a representation of Gal L over K, then all I have to do is tell you what it's doing on frob P, right? Because then I've told you what it does on every element. In fact, we need some... Well, while we're here, let me tell you... Well, yeah, why don't I tell you an infinite... Here's an infinite variant. Here's a variant for infinite extensions. The problem with infinite extensions is that they really will be kind of ramified infinitely many primes, maybe. So do we really want to consider those infinite extensions? Because are those actually, are they actually number theoretic? So it turns out that the only infinite extensions that I'll have to work with still have the property that they're unramified outside a finite set of primes. So I'll just set that. I think this is worth setting up while we're here. Here's a variant for infinite extensions. Let's have K a number field. Right? And now, just for simplicity, like when you do fundamental groups, it's easy to choose a point. Let's do the analogous thing. Let's just fix a K-bar. Fix an algebraic closure. Fix an algebraic closure, K-bar of K. Okay. And now, here's the problem. The irritating thing here is gal K-bar over K. This is too big, right? This is unramified. No, it's unramified at no primes. Is ramified at every prime of K. So that's not good. So somehow, if I wanted to try and understand representations of this group, and I wanted to understand a representation by saying where every element goes, this is somehow bad because I've just managed to concoct a group. We've got this great trick where elements have names, and now all of a sudden I've just thrown all those names away because the trick only works if you're unramified. So let's save us by let's fix some finite set S, right? Let S be some finite set of maximal ideals of OK. I have real... I'm always fussing about this non-zero prime. People often talk about primes of OK or prime ideals of OK, but I can't get away from the fact that the zero ideal happens to be a prime ideal by definition. And you don't really want to talk about zero. And so I always have to I have to write non-zero prime. I've just got sick of it now and written maximal. That's the same as saying prime but not 0. So let's have S be a finite set of problematic primes where we're not going to attempt to define frob P. And now let's try and make sure that if P is not in S, then let's try and make sure that we can talk about frob P. So it turns out that if K lives in L1 lives in K bar, and K lives in L2 lives in K bar, and these are finite, and if L1 and L2 are unramified outside S, i.e. that means if P divides the discriminant of Li over S, of Li over K, implies P is in S, right? So every prime divisor of every ramified prime must be in S. So I've got two extensions which are unramified outside S, then the compositum is 2, right? Then L1, L2 is as well. Then L1, L2 is unramified outside S. So we're in the situation where we can take the union, right? So let me define KS. K capital S, this is the usual notation. This is the union for L over K finite, and Galois if you like, Galois if you're paranoid, and unramified outside S. There you go. So there's a nice big extension. Take the union of L's. There we go. So this might well be an infinite extension. Not always, right? If S is empty and K is the rational numbers, then we'd be looking for an extension of the rational numbers which is unramified at every prime. And there's an old theorem that says that this is that KS would be K then, right? Every number field is ramified at is ramified at a prime. Every number field other than Q is ramified somewhere. So this KS, if S is empty, it could be finite. Actually, it's an interesting question. If K is a random number field and S is empty, can this be infinite? And it turns out it can. These are called class field towers. There's an article by Gollod and Shafarevich. Maybe while I'm here, kind of dumb example. If S is empty and K is Q, that implies that KS is Q. Kind of crazy example. If kind of K is sort of Q, the square root of -2 times 3 times 5 times, there's some random, this is finite, but I forget where you have to go up to, like hundreds. So see Gollod and Shafarevich. And then S can be still empty, and KS can still infinite degree. Go up to, I don't know, go up to for all p less than 1 million. That'll work. There. This is. I hope this is true. It might not be true. And I can't spell Shafarevich. I've got to be careful. You never heard that, Ivan. Let's go. I think I cover my tracks if I spell him that way. Is that right? Have I done is there any Russian speakers? Have I just done a terrible thing? I should have looked this up. There's Gollod Shafarevich. Anyway, let's do a much more sensible example. Let's do. Here's another example that I can't particularly work out. Let's do K as the rationals, and let's just let S have one prime here, right? There. So I'll look at extensions of Q, and they have to be unramified outside. So P some fixed prime. And I don't really know what ks is in this case. I don't really have any good understanding of this ks. But I know for sure that this ks will contain, if I can think of a number field which is unramified outside P, then at least I'll be able to show that that's contained in ks. And your first thought might be, q root p, that sometimes works, right? Q root p, that's ramified at P. Doesn't look like it's ramified anywhere else. But it's not quite as easy as that, right? Because this is a square root of P, and there's some number 2 here that you should be worried about. And indeed, q root P is ramified at 2 sometimes. And when it is ramified at P, you realise you need to take kind of q root minus P. That sometimes fixes the problem. And then you get confused about whether plus root P or minus root P is the right thing. And then you realise that actually the thing you want is the quadratic subfield of q zeta P. That's the splitting field of x to the P minus 1. And you see that polynomial there, the only interesting number you can see is P, so it might well be the case that this is unramified. If you compute the discriminant of this, you get P to the P minus 2, I believe. That's not true if P is 2. P to the P minus 1, maybe? Oh, yeah, I've got a factor of, yeah, I see. I know what I'm remembering. The discriminant of this, this is x minus 1 times 1 plus x plus dot dot dot, plus x to the P minus, plus x to the P minus. The discriminant of that is P to the P minus 2. So anyway, so that number field, if you know something about discriminants, you'll be able to convince yourself that that number field's unramified outside P. And in fact, I can do even better. Instead of just using zeta P, I could just use powers of P. And more generally, and in fact, ks would contain q zeta P to the n for all n at least 1. So this is a huge extension, you see. I guess here's a more general thing. What about k is q? Let's just fix some n an integer at least 1, and let's just let s be the primes dividing n. P divides n, and then it turns out that so q zeta n. That's unramified outside S. There. And actually, I know what that Galois group is, right? Gal q zeta n over q. Gal q zeta n over q. That's canonically z modulo nz star. Actually, this is a good. There you go. Look, we've worked out this Galois group. We've got a name for this Galois group. This Galois group is canonically z mod nz star. And then S is the primes dividing n. So while we're here, why don't we work out some of these I wasn't going to do examples. Examples are supposed to be in review session at 4 o'clock. But while we're here, why don't I just do this example? We have some dictionary, don't we now? This example, this is unramified outside n. So if P is prime, right? If P in Z is prime, and P is not in S, i.e. P doesn't divide n, then there should be a canonical conjugacy class. Then frob P is some kind of canonical. This is just now a prime number now. That's not supposed to be a capital P. That's supposed to be a curly P downstairs. That's going to be a conjugacy class, a canonical conjugacy class in the abelian group in Z mod nz star. So conjugacy class is just a fancy way of saying element, right? A canonical conjugacy class in Z mod nz star. Do you know what a monad is? I don't know what a monad was over the weekend until I was wasting my time. And I just realised I'm using a monad here. I'm identifying elements of a set with one element subsets of that set. So there you go. You can do that. Logicians can do that using monads. You'll be pleased to know. But I think we just do it by functoriality. So if you believe that there's a canonical identification between elements of a set and one element subsets of that set, then FROB P is a canonical. So at the end of the day, what have I done here? Well, I've got a prime number not dividing n, and I've got to think of a canonical element of Z mod nz star. Okay? So, well, there's two choices, right? Because in an abelian group, if there's ever one choice, there's always two choices, right? That FROB P is either going to be P or it's going to be 1 over P, and it's P. Canonical conjugacy class in Z mod, and it's P, right? And it's, of course, P in Z mod nz star. How can you tell this? Because remember, what does it mean if sigma is in Z mod nz star? Right? If sigma corresponds to T in here, then by definition, sigma of zeta equals zeta to the power T, right? For all zeta such that zeta to the power n is 1. Right? Sigma zeta is zeta to the T, and so therefore, on residue fields, on residue fields, sigma of zeta will be zeta to the T as well. Right? But FROB P of x is, of course, just x to the P on the residue field. So we have to think of some T that when you reduce everything mod P, the map zeta goes to zeta to the T becomes x goes to x to the P, right? So therefore T equals P works. So there's a very brief sketch as to why that's just happened. So here's an explicit Galois group of global fields. Here I've realized it explicitly as something that's comprehensible to the human. And now we've got this machine that, given any prime number downstairs, other than those in a certain bad set, we've got a machine that, given a prime number, gives us an element of this. And it's the obvious machine. P goes to P mod n. And then the Chebotarev density theorem tells us that there's infinitely many primes in arithmetic progression, which is kind of cool. So that's why the proof of that. That's why that's true. This is sort of a random bonus fact for you. But what I really want to do is take the limit. So there's an example. There's some examples. But of course, Ks over K can, let's stick to this case. If K is Q and S is just one, and S is 1 prime P, then Ks contains Q zeta P to the n for all n at least 1, right? And so therefore that means Ks contains the union of these things, right? Q zeta P to the n for n at least 1. This is all going on in some fixed Q bar, I should say. And that's by definition, this is just notation, Q zeta P to the infinity, right? I'm not attempting, this is strange notation because zeta to the P to the power infinity, that's not an object, right? That can't exist by itself. That can only exist in that kind of phrase there, where it just means this. So don't try to figure out which complex number zeta to the P to the power infinity is. So there's that. And that means that, and therefore, gal Ks over K is going to surject onto gal Q zeta P to the infinity over Q. So this is Q, really, right? K is Q. K is Q, and S is P. And that Galois group there surjects onto this group. So you can see this is infinite, but it's actually also comprehensible, right? Gal Q zeta P to the infinity over Q, and that will be, by definition, the projective limit of gal Q zeta P to the n over Q. And that will be the projective limit of Z mod P to the n Z star, and that will be ZP star. The p-adic integers. So there's now an infinite Galois group, but it's surjecting onto something that we at least have notation for. So maybe it's not too scary. I say that. I think it's terrifying. Gal, that is a terrifying group, and don't let anyone tell you otherwise. That's a terrifyingly large group. I happen to have found some chunk of it which we can kind of understand. But there you go. But this machine should give us some Frobenius elements, right? If Q is, let's go with R. R is really the fallback option for prime number labeling. But I think we're in that situation now. If R is prime, it's a prime number. If R is a prime number, Maser tried to introduce capital N as being a prime number, but that's not going to fly here. Let's go with R. If R is a prime number, R is not P, right? Then I've just kind of indicated that frob R, which I was kind of trying to tell you that this was a conjugacy class, but because everything is abelian, and again, because we're in a monad, we'll be able to identify that with an element. If R is a prime number, R not equal to P, then frob R is actually an element of Z mod P to the N Z star, right? And that's gal Q Z to P to the N over Q. Frob R's in this is just R, right? It's just R. R in Z mod P to the N Z star. And you see everything is kind of compatible with projective limits, right? Take lim. There. And we seem to have got frob R, which now lives in ZP star, which is kind of cool. Because now, do you see what's just happened is that this is an infinite Galois extension, but I've still managed to come up with a Frobenius element anyway. And that was something we didn't have before. So now, in particular, this quotient here, we have Frobenius. This is an infinite extension, but we have Frobenius elements. So the general story, of course, if I've got K as a number field, and then S is some finite set of places of whatever they are, finite places of K. That's just another way of saying that's just another way of saying maximal ideals of OK, which is another way of saying non-zero prime ideals of OK. And some people talk about primes of K. I don't know, finite primes of K. S is a finite set of finite primes of K, by which I mean what I always mean by S. Then gal Ks over K is by definition this limit of gal L over K with L over K finite and unramified outside S. And what we get is for each prime that's not in K, we can go back to P now. Now we go back to curly P. Finite unramified outside S, and then for all kind of curly P not in S, we get a conjugacy class frob P, if you like, for L over K, just to be clear, living in gal. Oh, this is Galois. Is Galois, or else I can't make sense of Galois. It's all right for a random finite extension. You just replace it with the Galois closure. Frob L over P lives in gal L over K. No, conjugacy class. And these conjugacy classes glue together. It's one of these things. Do you remember I talked? If you believe that the inertia subgroup with its upper numbering filtration glues together well, then surely you'll believe that Frobenius elements glue together well, because that's a rather easier thing. We get some conjugacy class here, and these glue together. To produce a conjugacy class And that conjugacy class is now still called frob P there. And if you like, frob P, comma, Ks over K, we really want to keep track. And that is a subset of gal Ks over K. There. And it's a conjugacy class. And as I say, for a random K and a random S, this is some terrifying infinite non-abelian group. But this machinery at least gives us names for conjugacy classes. And you shouldn't expect any more than that, right? You shouldn't expect names for elements, because these Galois groups are in some philosophical sense only defined up to inner automorphism. So it's very difficult to somehow pin down an element. You can only pin down an element if you make choices, right? You might say, oh, gal q bar over q, that can take, like, complex conjugation, right? Let k be q. Complex conjugation, that's bound to be in that Galois group. But when you think about it, complex conjugation is only in that Galois group if you choose an embedding of your abstract algebraic closure k bar into the complex numbers. And of course you can do that, but different choices give you different complex conjugations. And you end up with a conjugacy class of them, you see. That's what happens. So it's impossible to write down elements of Galois groups for philosophical reasons. Anyway, but we can write down conjugacy classes, and then what does the Chebotarev density theorem say? Chebotarev density theorem for finite extensions said that this map here, P not dividing S, conjugacy classes in gal L over K, that thing there was surjective. This map here sending P to frob P. It says that map was Chebotarev. There's missing accents. Sorry, family of Chebotarev. I forget where they go. They're sort of strange. I should revise my Cyrillic somehow, shouldn't I? Chebotarev density for finite extension says this is surjective. Chebotarev density is the statement that the density of primes that hit a certain conjugacy class is the size of the class over the size of the Galois group. But for this infinite extension, that story doesn't apply. In fact, for infinite extensions, I can prove that typically this map won't be surjective, because we had some example here with these q's e to p to the n's, where this was an uncountable infinite group, and that's only a countable set, right? So for infinite extensions, Chebotarev density can't possibly say that some map is surjective. But it's surjective at all finite levels, which is, when you think about it, a way of saying it has dense image. So as a corollary, is that if L over K, is infinite Galois, is an infinite and Galois, and it's unramified outside S, as S the usual thing, S a finite set of finite primes of K, then the conjugacy class is frob P for P not in S. These are a dense subset. Maybe I'll take the union of the conjugacy classes. The union of the conjugacy classes, this, living in Galois, right, is a dense subset of gal L over K. Okay, so that's what we lose when we go to the infinite extensions. We lose precise Chebotarev density that tells us exactly how many primes less than x are going to be frob P for our given conjugacy class. But we just get, this is now terrifying infinite group, but we know that a dense set of conjugacy classes have got names. So you see a corollary is, if I want to understand a map, if I've got some map f from gal L over k to x is continuous, right, then we might be able to, then we may well be able to recover f from the data of f of frob p. Well, if f is continuous and constant on conjugacy classes, there. So we've got a continuous map that's constant on conjugacy classes. We may well be able to recover that map from the data of f of frob p, right? There, for p not in S. That's the whole point. This is what you need to know. This, you know, it's kind of always good. If I do something technical and you kind of slightly lose track of something, then it's kind of important to know what you're supposed to be taking out of this discussion. And what we can take out of this discussion is if I've got a representation of a group, then a general fact says representations of groups tend to be quite well behaved on conjugacy classes. So if f is something like characteristic polynomial of a representation, then f might well be constant on conjugacy classes. If I'm trying to say something about what this representation is, then maybe I just need to know about the characteristic polynomials of Frobenius. That's what you need to take out of this discussion so far. I think we're ready to start talking about representations. I am. Right, great. So the other fact we need to know is Brouwer-Nesbit. Bless you. Oh, Gesundheit you're supposed to say here, aren't you? What's with the German thing? Why do I know that you say Gesundheit? Because I saw, like, Oscar the Grouch say it to somebody when I was about 5. Brouwer-Nesbit. The Brouwer-Nesbit theorem says the following great thing. So this is true for arbitrary groups and arbitrary fields. So let's let G be a group, and let's let E be a field. There. So recall that a representation rho from G to GLN of E is said to be semi-simple if rho is a direct sum of irreducibles. There. I don't know if this is a very helpful thing to say, but the zero-dimensional representation is semi-simple because it's a direct sum of no irreducibles at all. And then every irreducible representation is semi-simple, and then direct sums of finitely many irreducible representations. Semi-simple too. That's another monad. Right. I know what a monad is, and now I can see them everywhere. Anyway. Right, so Brouwer-Nesbit says the following thing. If rho 1 and rho 2 are maps from G to GLN of E, are two semi-simple representations, and if they have the same char poly, and if for all little g in G, rho 1 of G, well, I need maybe, let's write char poly of rho 1G equals char poly of rho 2G. So we've got two abstract finite dimensional representations of an abstract group. Could be infinite, no topology, might not be continuous. This is an algebraic statement. I've got two representations that have the same char poly, and they're both semi-simple, then they're isomorphic. That's the punchline. Row 1 is isomorphic to row 2. Then row 1 is isomorphic to row 2. So the proof is just algebra, right? I mean, it's quite tricky. Yeah. And I'll also remark that if you replace GLN of E with a random group, for example, an L group, and you take random maps, row 1 and row 2, from G to this random group, and if you just ask that for all G, row 1 of G is conjugate to row 2 of G, then the conclusion doesn't hold. And that's why if you have general automorphic representations, they might not be determined by their local components. So anyway, there's Brouwer-Nesbitt. So maybe I'll sort of say warning. Fails analog for general H instead of GLN of E, you took some random group homomorphisms G to H, so it fails. You can get two homomorphisms G to H which are locally conjugate without being globally conjugate. So this really is a statement about representations. It's a shame to have to work out the entire char poly, because sometimes with representation, when you do undergraduate representation theory, you tend to just take traces, right? And you learn very early on that if E is an algebraically closed field of characteristic 0, then the trace of a representation is a very powerful invariant. And the reason that traces are so powerful as an undergraduate, but now I'm demanding characteristic polynomials in Brouwer-Nesbitt, is because if you know the trace of everything, then you often know the characteristic polynomial of everything, right? Sort of remark, if the characteristic of K is 0, if the characteristic of E is 0, which of course it often is in this course, then it suffices, then the trace of row 1 equals the trace of row 2 already implies that row 1 is isomorphic to row 2. These are still both semi-simple, obviously. If I drop semi-simplicity, this is kind of trivially false for trivial reasons, right? Row 1 and row 1, take a non-semi-simple representation. I mean, if G is finite, there aren't any, right? But for a complicated infinite group, if I take a non-semi-simple representation, it's kind of like, it's got this as a sub, and this is a quotient, and then there's some random stuff in the upper right-hand corner. And then row 2 is the semi-simplification of row 1. It's this at the top, this at the bottom, and all that stuff is zeroed, right? So kind of whatever, chi1 star 0 chi2, and chi1 0 0 chi2. Those, you could imagine that's notation for two representations of a group. This one's not semi-simple. This one is. They've got the same traces, the same char polys and everything. So that's why you need semi-simplicity, because you can't control the stars if you just know about traces. So why are these the same? Because as can compute the char poly of G, the char poly of a random matrix, char poly of row of G from the trace of row of G to the I, right? Of G to the I for 0 less than root of I less than root of n, I guess. Maybe less than root of n minus 1. But you can only do that computation if you're allowed to divide by n factorial. If dividing by n factorial is okay. That's basically the idea. Is this true? Do I have to go up to? I think I might have to go up to n. Let me go up to n. I like the idea of starting at 0 because I can recover the dimension. But I need n anyway. Let's go with 1. There. So, and in fact, this gives you a. If you want to, I guess, for a complete understanding of Brouwer-Nesbitt and this consequence here, you could do some example. Here's a non-example, right? Let's have G is cyclic group of order 3 there, and let's have E is the field with 2 elements well, let's have an algebraic closure of the field with two elements, because representations over algebraically closed fields are nice and easy. And let's have n is 2, and find non-isomorphic row 1 and row 2 semi-simple and reducible, such that the trace of row 1 equals the trace of row 2. I'll give you a hint that they're both the zero function. So representations aren't always determined by their traces in the annoying situation where you can't divide by n factorial in your base. If n factorial is invertible in your field, then you're going to be fine. But n is 2, and 2 factorial is 2, and 2 is 0 in this coefficient field E. So Brouwer-Nesbitt fails in that. Well, I don't know. I just found this. I found this as an illuminating example. Once I'd done that example, I've never forgotten the statement of Brouwer-Nesbitt. That's the point I'm trying to make, because it reminds you of what can go wrong. Right. So there's Brouwer-Nesbitt. Right. So what's the upshot? Upshot of all I've said today. Of everything I said today. So I've got some L-adic representation, rho from gal k s over k to g l n of, let's say, E, where E is... Now, if these are representations of global Galois groups, then probably E is going to be some extension of QL. Some finite extension, right? So E is some L-adic thing. This has some L-adic topology. We'd better see examples of this because this suddenly looks terrifying, doesn't it? But these are the things that show up in nature. This is my Galois group with its profinite topology. This is a continuous semi-simple representation. It's a continuous semi-simple representation. If you're worried about semi-simple, don't worry, because all the rows that show up in practice are irreducible. So a continuous irreducible representation, if you like. If I've got a continuous semi-simple representation, and if I happen to know the characteristic polynomial of rho of Frobenius, and if I happen to know the char poly of rho of Frob P. I've done a monad thing again, right? So Frob P is a subset of gal ks over k. So rho of Frob P is, if you like, it's a collection of matrices. But all the things in here are conjugate. So formally it's true that all the matrices in here are conjugate. So they've all got the same char poly, right? If I happen to know that the char poly of rho of Frob P, maybe make some remark. This is a well-defined polynomial, right? Whatever fp, and it's going to be in E of x, right? So even though Frob P is a conjugacy class, not an element, it still makes sense to talk about char polys. They'll be well-defined polynomials. So if I happen to know the char poly of rho of Frob P for all primes P not in S, for all P not in S, then I know rho, right? Then rho is uniquely determined by this data. And that's because rho is continuous, so the function sending an element of the group to the characteristic polynomial of that element, that's going to be continuous, right? you think about it. And Brower Nesbitt says to know rho, it suffices to know that function, sending an element of the group to its char poly, to the char poly of rho. And if I happen to know what the char poly is on Frobenius elements, and this is what happens in number theory, you often know char polys on Frobenius elements, then by continuity, there's at most one way of extending that to a map on all of that Galois group. And so by Brower Nesbitt, there's at most one row that can have these char polys. So if we're given a row, then we know it automatically. Right? So in particular, if I claim that a representation exists, and I tell you the char poly of every single Frobenius element, then I've told you what that representation is. Right? Of course, there could be no such representation. But if I'm asserting that a representation exists, then all I have to do to uniquely determine it is to say what's going on in these char polys. That goes there and that goes there. I didn't do this one yet. Great. Let's do an example. Let's do the cyclotomic character. Let's do K is Q, and let's do. Let me just define. Let's let S be P. And let's let L be Q z to P to the infinity. There. And now, I'll remind you, so this is the union of Q z to P to the n. And so that means that gal L over K is a projective limit of z mod P to the n star, and that's zp star. And do you know what we can do? Zp star is GL1 of Zp, right? Is GL1 of Zp. Oops. And so that lives in GL1 of QP. So if you think about it, we have something here, right? So we could look at the following representation. I'm going to talk about the scary gal Q bar over Q, I think, because that's what people often do. But gal Q bar over Q is scary because we don't know the names of any of the elements, right? Then here is, I mean, it's a miracle that we can even define anything on this gadget, right? So gal Q bar over Q, there is a group. I used to be scared of objects when I couldn't write down any of their elements, but you kind of, it's kind of an interesting, I was telling some of this story already. There's this thing called B de Rham. And you meet this when you're a graduate student. And in my case, the way you meet it is you're a graduate student and there's some bloke called Fontaine who's giving a talk at the Newton Institute. And you go along and he spends 45 minutes going on about B de Rham and then 10 minutes kind of frantically sketching some proofs of some theorems about étale cohomology. And it overruns by about 15 minutes and gets covered in chalk and then apologizes because he says he has to spend 45 minutes defining B de Rham every lecture he gives. And nowadays, people are even worse because they assume that everyone knows what B de Rham is. So I don't know what B de Rham is, but the thing is, what happens over the years is you see so many people talking about B de Rham and writing down basic properties of it. After a while, you don't get, you're not scared of it anymore. You end up in some sort of symbiotic relationship with it. So, B de Rham doesn't trouble me, and I don't trouble B de Rham. And there's some short exact sequences that occasionally I see, but I know they're true. Right? So the same is true of gal Q bar over Q, right? That's a group about which I know nothing. And yet I will happily work with it because somehow the fact that I know nothing about it just doesn't bother me because I'm going to turn it into something I do understand. So by the fundamental theorem of Galois theory, that surjects onto Gal Q z to p to the infinity over Q. And that's a group I do understand because that's canonically isomorphic to Zp star, and that goes into GL1 of Qp because it does. So there's a one-dimensional Galois representation, right? But this group here, this doesn't have any elements that I can't possibly evaluate this anywhere because I don't have a name for any element here. But remember, this does go here to Gal Q S over Q, right? With S is P. I don't even understand this, right? I don't even understand the maximal extension of Q that's unramified outside P. Because it certainly contains this, but then there's a whole bunch of abelian stuff, right? Some of these, if P is an irregular prime, then these things will have non-trivial Hilbert class fills, and those are unramified, so those will certainly be, these are unramified everywhere, so they'll certainly be unramified outside S. So this is probably some very complicated non-abelian group that's kind of closely related to Gal QP bar over QP, I guess. So this goes here. I don't really understand this, but at least I know that this stuff in here has names, right? I've got names for conjugacy classes in here, right? This contains conjugacy classes. Maybe I'll put a sub, right? This contains frob R for R, a prime of desperation. This maps onto this, right? So this Galois group here, which is now abelian, contains a whole bunch of conjugacy classes called frob R, which are now kind of elements, right? So frob R, that's now an element. So it's in here, but R is all I know about R is it's not P, right? Because R is not in capital S, so it's not P. And of course, frob R is just equal to R. So there's a complicated one-dimensional Galois representation called the cyclotomic character. Rho is called the p-adic cyclotomic character. And it's characterized by the fact, and by Brouwer, Nesbitt, and Chebotarev, by BM plus. So does he have a little hat there? I don't even know. There's a nice little thing in the middle one to put your chalk, and you just put it there anyway and it falls off. But Brouwer, Nesbitt, and Chebotarev, this rho is classified, well, rho is determined by the fact that rho of frob R equals R, right, for all primes R not P. There. So there's an example that probably loads of you have seen before, so apologies if I was boring you. But you know what? Actually, there's more to this. There's something kind of crazy about this example. Because let me show you a kind of a variant of... I knew this for a long time. But now let me tell you something that I didn't know and didn't even realize I didn't know. Is that... This still blows my mind, actually. Let me. This is the p-adic. I need notation for this, don't I? Let's call the p-adic cyclotomic character. Let's call the p-adic cyclotomic character rho. No, let's call it chi p. That's a really good name for it, I think. That might not be a good name for it. Let's call it omega. That's a terrible... let's call it that, because I want to use chi to mean loads of other things, and I don't want to confuse things. Omega p, this is non-standard terminology, but it just works for me. The cyclotomic character is often called chi, but I'm going to spend most of the next lecture going on about random characters chi, none of which will be the cyclotomic character in general. So I want to reserve chi to be I need chi to be a variable later, so I really want to stay away from chi. So let's call it omega p. Right, here's quite a confusing thing. Let's choose two different primes. Let P and L be two different primes. Right. This whole lecture was supposed to be completely trivial apart from this last bit. Let P and L be two different primes, and let's let S be the set P and L, right? Okay. And now, here's a representation. Let's do omega P. That goes from gal q bar over q to gal qs over q, maximal complicated extension line ramified outside P and L. Okay, and that just surjects onto whatever, gal q, I'll do omega p, so z to p to the infinity over q, and that goes to zp star. So there's my, let's go up here to give me some space. That's going to go up there to gal qz to p to the infinity over q. And that's going to go to zp star. Hopefully I'm about to teach you something. There's omega p, and now of course we've got omega L as well, right? Omega L, gal q bar over q, surjects onto blah blah blah, gal, well I will write it in, q zeta L to the infinity over q goes to zl star. There's two different representations of gal q bar over q. And it's not some weird pathological thing, right? They both factor through this, right? Gal qs over q. They both factor through that that is a sensible Galois group. I don't really understand it, but we've got names for the elements, right? If R is a prime of desperation, then there's frob R. If R is not equal to P or L. There's frob R, which is a subset. R is a terrible name for a prime, I do apologise. Then there's some subset of this Galois group called frob R, right? So note that this frob R, these things here, for R not in S, give a dense subset. Right? The unions of the frob R, the unions of these frob R's give a dense subset of gal q s over q. And omega p and omega L, right? Omega p of frob R is equal to R, right? And omega L of frob R equals R. Okay, so omega p and omega L are two Galois representations that are exactly the same on every single frob R, right? So they are equal on some dense subset, so therefore they must be equal, right? By Brouwer-Nesbit. Want Brouwer-Nesbit to imply that omega p equals omega L, right? Because they have the same traces. But Brouwer-Nesbit doesn't apply. Okay, but this is no good, right? Because Brouwer-Nesbit is about two representations, to GLN of E, where E is some fixed field, maybe with a topology, Brouwer-Nesbit is about two representations to GLN of E. And we have two different E's, right? One of our E's is QP, right? And the other is QL. So Brown-Nesbitt doesn't apply. So even though we've got two representations with the same trace, they're to different fields, and they're continuous with respect to different topologies. So you can't use Brown-Nesbitt, and that's not surprising, because omega p and omega L are completely different. They have the same traces, and yet they are completely different. They cut out, their kernels are utterly unrelated, right? So in fact, kind of omega p and omega L couldn't be more different, right? Couldn't be more non-isomorphic, right? Because let's look at the pictures. Here's the kernel of, there's Q. By Galois theory, you have the kernel of a representation. It cuts out some, the kernel of representation is gal Q bar over a sub. Gal Q bar over L, where L is some random field here, right? So this is the kernel. The kernel of omega p is somehow q z to p to the infinity, unramified away from p, totally ramified at p. And here's the kernel of omega L. This is q z to L to the infinity, right? So what's going on here is something really mysterious. It's that Brown-Nesbitt says that a representation to GLN of QP is determined by its trace, but this crazy example shows that you can have two completely different representations to completely different GLN of QPs, GLN of QP, GLN of QL, and they might have they might look like they've got the same traces, but they're not isomorphic at all, right? These extensions are not the same extension. These are totally disjoint, right? Anything in this field and in this field will generate an extension of Q, which is unramified outside P and unramified outside L, so it's unramified everywhere. And so it must be in Q. Those extensions are totally disjoint. These representations are nowhere near isomorphic, and yet we've just proved that both of them send from R to R and then extend by continuity, right? But the continuity, the topologies are totally different. So that's just that's not something that's stressed. I'm going to talk about compatible sequences of Galois representations in the next lecture, and this is your first example. But when I was your age, I thought that there were some completely false things, and so let me completely disavow. Is that the word? Something you of those completely false things before we even start. Right. See you in 15. I didn't do anything in this lecture. It's just all definitions and basic properties. So hopefully not too difficult to internalise.